introduction, I'd like to introduce Dr. Hathaway, who will be introducing our speaker. Dr. Hathaway is our professor of organic
Thank you, Dr. Moore, for this great honor.
You're very welcome. Much deserved.
Our speaker today is someone I met a little over about 3 years ago or more. He was born in South Bend, Indiana. He moved here when he was 6. He started at Laterno. First met him when he was doing visits about, to see where he wanted to go to school. So I had a chance to talk about what we do here. Decided to come here. He's majoring in chemistry with biological emphasis. And one of the highlights of his academic career here is he survived organic chemistry with me.
Yay!
And he hopes to survive the PChem with Dr. DeBoer.
Tomorrow.
And so anyway, he's finishing up. He'll be graduating this spring and still looking at graduate school options and things like that. So today he's going to be talking to us about 2 sets of research he did with me one summer and research he did with Dr. DeBoer another summer. So I present to you Darby Ball. Let's give him a good welcome.
Thank you, everyone. As you've just heard, I'm Darby Ball, and today I'm going to be presenting zapping reactions and imagining new lithium-ion batteries, which is some examples of practical and theoretical chemistry research done here at LaTourneau University. First, I'm going to be discussing my organic chemistry research I did in 2015 with Dr. Hathaway. The problem: many of you may recognize this apparatus over here on the left. That's a round bottom flask attached to a condenser, and that's used for reflux. Basically, a low boil occurs in the mixture at the bottom. The vapors come up and they condense along the water-cooled glass, and that drips back down into the solution, so you allow it to boil without boiling off. However, these reactions can potentially take a while, and this can be bad for a lab environment. Long labs of sitting around waiting for reflux can be boring to students and can waste their valuable lab time. You don't want to be spending a third or more of your lab time just watching that bubble. So, we decided we wanted to investigate a potential solution. This would be a method to speed up our slower reactions while still being safe and affordable. Likewise, we also want our reactions to still give a comparable yield and purity of product. The solution that Dr. Hathaway devised after reading in the literature was refluxing in a conventional microwave oven. So we took this microwave oven, bought at a normal store, cut a big hole in the top of it so we can put a glass tube through it. We shield that with copper tubing that goes around it, as you can see right here. That prevents us from shooting microwaves out and boiling ourselves. We likewise have this plate here to hold that in place, and we've got aluminum foil above and below on the inside to add further shielding. Above the glass tube here, we have a condenser where water runs through, cooling the vapors, allowing them to condense and coming back into the microwave. Fun stuff. So first, I'm going to discuss some of the techniques that we use to identify our products. Those of you who are currently or have taken organic chemistry will know these very well. First of which is melting point determination, done with this machine here. You just see what temperature a solid product melts, and if it's a small range, that indicates that the product is more pure. The other techniques I will be discussing in future slides, so I'll cover them as we get to them. Thin layer chromatography, or TLC, is done to show purity of a substance. Materials are placed on a silica gel on top of a plastic sheet, placed at these X marks here. So for example, you could put your starting material here, then your reaction mixture in the middle, and then a final product on the right side. A solvent is drawn up through the plate using capillary action. The solvent interacts with the substances that are on the gel and moves them a different distance depending on how well they interact. Therefore, this causes separation between materials that are in the same location. This can show if your product contains any starting material. So here you see the starting material that still exists within the reaction mixture, as well as some intermediate, as well as some final product, but by the end you only have final product. And this can be shown, it can be used to show that there's nothing else contained in the reaction mixture. Another technique we use is FTIR. That stands for Fourier Transform Infrared Spectroscopy. The peaks that are produced when you run this correspond to functional groups in the molecules, as you can see by these convenient arrows I've drawn here, demonstrating some of the peaks for functional groups. This is quick and easy to perform. It gives you some good information about your product, whether it contains the group that it's supposed to or if it has something that it shouldn't have, and does not degrade or destroy your product, so you can just pick it back up off the machine and it's still fine. Then we have hydrogen NMR. This one's my personal favorite, as it's generally the most useful for organic chemistry, tells the most information. These peaks that you produce here correspond to hydrogens in the molecule, as well as a standard peak that you zero. These peaks can be integrated here to identify the the relative numbers of hydrogens contained within your molecule. So, for example, this peak here integrates to slightly over 4, but it's going to be a whole number, so it corresponds to these 4 hydrogens on this benzene ring in this malamide. Well, this peak here integrates to 2, and that corresponds to these 2 hydrogens here. Picked a nice simple molecule, so we didn't have too many peaks, but you can get the point. This isn't as fast as FTIR, but it gives more information. It's also not destructive, although you do have to dissolve your materials in a solvent, so it's not as simple or quick to do. The main set of reactions that I focused on is the preparation of substituted N-phenylmalamides and their Diels-Alder reactions with anthracene. That might not mean much to you, but here is the final product that we make using this reaction sequence, where R can be any set of functional groups coming off of any of these points of benzene, such as chlorine, or a methyl group, or methoxy. You get the point. So the last step of this set of reactions calls for an hour of reflux at a very high temperature. And understandably, it's not fun to sit around waiting for an hour to watch this thing bubble and sit there. And a lot of time we'll have other things we could do during that lab time, but that doesn't take away from the fact that this is a very long section of this lab. So I performed this reaction sequence, and I compared the results of doing this with normal reflux with a microwave reflux in our modified apparatus for the last step. Here I have your malamide reaction sequence. We formed the malamide using 2 steps, which isn't too complicated. And then we react it with anthracene here in dilime at a very high temperature, and it forms this Diels-Alder product. And this step I vary between reflux and microwaving. So here I've got a comparison of our methods. On the right, I've got a table of theoretical and then practical yields that we've gotten on single trials for this, so don't take these as definitive, but it's indicative. Normal reflux was performed for for a full hour, while microwave reflux was performed for 2 3-minute periods with 1 minute in between for cooling so it didn't completely boil over. You can see that it gave comparable yields over here in our columns, although you can see that the reflux yields were far more consistent than our microwave yields, some of which were high, others were kind of low. But again, this is only done for 1 trial run through each just to see they can be done. These microwave products that we observed did appear to be as pure as reflux based on their TLC and NMR data, which did not show significant impurities. However, not all reactions ran so smoothly in the microwave as I was to find out. I ran several other series of reactions, one of which was the preparation of tetraphenyl cyclopentadienone, which is one of my favorite mouthfuls from organic chemistry. It's a pretty simple reaction, as you can see, just combining these 2 materials to get your product. The reaction normally calls for 20 minutes of reflux in ethanol as the solvent, which, as you may or may not know, has a fairly low boiling point. So when I put that in the microwave, I flipped it on, and it caused fumes to quickly boil out and go all over the lab, where Dr. Fernand's group was working, and that was very rude and inconvenient to me, so I had to quickly shut it off and change what I was doing. So I switched to ethylene glycol as my solvent due to its much higher boiling temperature, so I wouldn't have it boiling up faster than it could condense back into the solution. However, this did cause some problems. Rather than getting a nice, beautiful purple crystal, as it comes out to be, I was getting this, which is an ugly black tar that refused to evaporate or solidify and was worthless. So, it didn't work. Some conclusions I've drawn from this: the microwave worked well for reactions that required high temperature. Specifically, it may have worked very well for the Diels-Alder reaction with anthracene, because anthracene itself might have been able to absorb microwaves from the oven, aside from just the solvent itself, which would cause it to heat faster than the solvent itself and react faster. So it could do this in a matter of 5 minutes rather than an hour. Low boiling solvents cannot be used with the microwave apparatus, as they can boil much faster than this will condense them, and they'll go out the top and spew alcoholic fumes all over the room, which is bad. And then some reactions due to that, and possibly due to the addition of different solvents, did not work well with these very high temperature conditions in the microwave. And instead of doing the reaction, they cooked into something else. In 2016, I spent a month doing computational chemistry research with Dr. DeBoer, which was fun. So, our subject was lithium-ion batteries. And you might ask, why batteries? Batteries help to take advantage of cleaner energy sources, such as wind or solar power. But when production for those is higher, especially during the daytime, than your demand, you need a place to store the excess power so it can be used at night when you don't have enough production. Likewise, we want it for use in high-efficiency electric vehicles, which could potentially go thousands of miles if we could have a good enough battery. So, lithium-ion batteries are currently those that have been found to work best for this set of parameters we have on batteries. They're unique in that lithium ions travel from the anode to the cathode as well as electrons moving, whereas in most battery systems you just have moving electrons. The anodes that are generally used are graphite. The cathodes that are generally used in lithium-ion batteries are transition metals. And generally there's a lithium-ion conducting electrolyte, which is generally an organic solvent in most batteries that you'll see. So, we wanted to focus on the lithium-ion battery electrolyte. Currently, these organic liquid electrolytes correspond to those cathodes and anodes that I expressed. They are flammable, which is bad, and they have a limited operational temperature range. They freeze or evaporate. It's not going to work. It's going to mess up. Likewise, they allow for dendrite growth, which is when lithium ions form together back into a metal, and those metal form thin lines that travel throughout the battery. If those can connect to the anode and the cathode, it will cause the battery to explode, as you may have seen last year with Samsung. So that's bad. One advantage that they do have, though, is that they're very fast at moving these ions. They're very good at moving them. We want to compare that to solid glass electrolytes. These can be used with a high-power solid metallic lithium anode, which is a much more efficient system, although also more dangerous in a liquid solvent. We're avoiding that. It can utilize an air cathode, which has an order of magnitude higher capacitance, and also very energy dense because it can use air from surroundings rather than being contained within the battery. But I'm not here to talk about that. It also, more importantly, it has a less flammable solid electrolyte, so you're not risking exploding like that. Likewise, it has a large temperature range because it's solid, and there's no risk of dendrite growth. The main problem that we're encountering is that ions don't move very fast through it. So the goal of this project is to increase that. So the question becomes, how do we increase the mobility of these ions in our solid-state glass electrolytes without degrading the structure of the glass electrolyte? We take advantage of the mixed glass former effect, as demonstrated in these diagrams below for a germanium glass, in that a glass is more permeable to ions when it is a mixture of two different glasses and ends up having a greater permeability than either glasses by themselves, which is good. So we decided to make an oxysulfide matrix. Lithium, a pure sulfide glass, is shown to have a very high lithium ion mobility, especially compared to silica, but it's also unstable, which means it explodes, so we're right back to where we started. Therefore, we want to make a matrix that has the safe properties of our silica normal glass, as well as the permeability of these sulfide glasses. So we're deciding to make a matrix with a variable amount of each of those materials, and go from there. Previous work has been done here at LeTourneau, I think by the Hoyts, on molecular dynamics studies on lithium silica system in conjunction with Iowa State University. As shown in this data on the right, they performed some calculations in LAMMPS, which does small timescale molecular modeling of lithium ions in an electrolyte. But this called for the need of precise pairwise potentials for these sulfated systems, rather than just silica. So that's where I come in. I decided to base my work off Habasaki's, which was, well, he's a Japanese guy who did a lot of work over this in the 90s. His system for doing this was to make tetrahedral clusters of a silica system. Excuse me. Tetrahedral clusters of a silica system within a crystal. He would imitate that by putting these positive charges out here to represent other atoms. This would guarantee charge neutrality and mimic being in a crystal. Then I would hold these charges at the equilibrium bond distance away from these oxygen, so they would be the same distance between here and here. And I would do that both for oxygen and for sulfur, but with sulfur would be a longer bond distance. So just here I've got an example cluster that's a pure silica system with those 4 positive charges out there. And this is what I did my work with. Working with Gaussian and Gauss view, I would build my clusters in Gauss view and then transfer them over into this system of Gaussian 09, where I would run my calculations. And I would also have to input my charge and multiplicity of the system, which you don't need to worry about. And I would also manually input those point charges, which turned out to be a problem. Initially, my data did not match my references, because first I was just trying to copy his results and see if I could get the same thing. And I found out my data was not working at all. I was getting these weird curves out rather than a nice U-curve around the equilibrium point. I found that my problem was my charges were static rather than moving with the oxygens as their bonds were changed. I solved this issue by varying the charge locations to remain at equilibrium distance away from the oxygen atoms. This created a new lesser issue though, because I was varying the charge locations every time. I had to manually enter those every time with new coordinates. It became a bit of a pain, but I found a way to expedite it using Excel. Basis sets, I probably don't need to talk too much about this. Basically, using more equations gives better data, lower energy. For example, I've got 2 basis sets here. This one's slightly better, but also takes about 5 times as long to run. So whereas this might take 3 minutes, this will take 15. So you gotta be careful about your time usage, but you do want to get good data. So I did several types of calculations, all of which were for absolute energy, but I varied several things. First, I was varying all 4 bond lengths, maintaining a tetrahedral symmetry. I vary these R factors equally and simultaneously. I also would vary 1 single bond at a time while keeping the others constant, and this maintains their bond angles as well. Lastly, I varied their bond angles without varying their bond lengths, and I varied these in pairs. The reason I did all these symmetry operations was so a lot of these numbers would end up being the same, so the interactions between here and here are the same as here and here, for example. This is all the sets of data that I calculated using all these symmetries for these various systems with varying amounts of oxygen and sulfur in them, and I got a bunch of nice symmetrical, mostly symmetrical, U-shaped curves for these around their equilibrium point, which is good. Using this data, I fit these to Gilbert-Iter potentials, which are this lovely, fun, long formula here that I don't need to explain, and as a matter of fact, probably couldn't, but involves these 3 parts. And this is a set of pairwise interactions. So, for example, I've got 5 atoms here, so therefore that goes to 10 pairwise interactions. This between each of the other 4, then this between the other remaining 3, etc. So that ends up being 10 different pairwise interactions that I add up to get the total energy. Which, in short, gives me nice values for A, B, and C for each type of atom in the system. Fun stuff. Future work, these pairwise potential parameters can be used in molecular dynamics studies in LAMPS program or other programs. This can be used to model lithium-ion mobility in various oxysulfide glasses. This can lead to a determination of the optimal composition that has the greatest permeability while also still being safe. And this could lead to physical testing and application. I'd like to give acknowledgments to Dr. Bruce Hathaway for taking me on, and then Dr. DeBoer for taking me on the following year, as well as his partners at Iowa State in their project. And then thankfully the Welch Foundation for paying me to do this, which was lovely. A great quote to go with this is, "Be a scientist, save the world." Thank you for your attention.
Have any questions for Darby about any of this?
How did you, did you were just like, oh, I'm just going to use the microwave to see what happens, or how did you get started in working in both of these projects?
Okay, well, they were done with separate years, and the first one with the organic project, it was in class. Dr. Hathaway just asked me if I wanted to stay on and work here during the summer because he knew I'd be in town because I live here. So I did that. As for the microwave project, there had been work done in the 80s and on involving modified microwaves, so we decided to see what we could do with that here and potentially improve the organic lab sequence.
I didn't ask him just because I knew he was going to be here. That wasn't the only reason.
It's not a requirement.
When you switched compounds with the microwave and you got that useless black sludge,
Yes.
was there no way to get out what you wanted from it? Like, why couldn't you use it anymore?
I tried actually, but I actually did manage to get everything to evaporate, but it was still a brown sludge rather than a purple liquid, and when I tried running it in the NMR, it was a bunch of junk data. It was a mix of various compounds. Basically, the reaction had done something else that didn't give me what I wanted. It might have been a bonding between the materials and the solvent, because I used a different solvent there. I don't know if it reacted, but it might have. But I didn't spend too much time investigating that because it seemed like a dead end.
Okay.
So now that you've done this, what would you tell other people who are thinking about doing research here?
I would definitely say get involved with it. It was fun. It was intense. I wasn't doing anything else for the month, and I got paid well, so that was lovely. It was great just to work with the professor, who's always there just to give you a heads up, say, hey, this is what you're doing. If you have a problem, you go talk to them. They're really open and nice about that. And we had fun discussions and lunch with each other, and then we'd get together with groups of all the other researchers and do stuff. That was great. This is a great 4 weeks, and since I wasn't doing anything else during May, it was a great time.
Any other questions? Well, if you're too shy to ask a question here in a big group, we're going to be going down to the Corner Cafe and eating lunch, and so you feel free to join us down at the Corner Cafe. Let's thank Darby again for his time. And you are dismissed.
All next week.
Seems like I ran a bit faster to do that.
By a little faster. They don't want it.
Good job, Darby.
Thank you.
Good job.